Hi. So as you can see, I'm now at Macquarie University. I did that just to mess with everyone. I changed just like a month ago. So anyway, so thank you to the organisers for inviting me. It's been fantastic for an engineer to sit in a room full of physicists, and I'm telling all my friends. And I've learned a lot, and it's great to be sort of sitting at the beginning of something which I think is going to be pretty awesome. So I'm going to talk about stochastic computing systems, but I thought since I'm the only kind of flag waver for CMOS here, I'll give a bit of a historical background, just a small one, not very long, just about where sort of neuromorphic sort of comes from and sort of what we've done, you know, in the last few years. There we go. Yeah, so I'm going to talk about neuromorphic engineering, just some early work, just where it came from and why people had crazy ideas long ago, and we're still having the same crazy ideas, so it's excellent. A little bit about my work, because it gives a little bit of an idea of why I kind of hit my head against a wall and decided I wanted to embrace noise. And then some ideas about stochastic electronics. And I really just included some interesting algorithms that show using noise and mismatch can be useful in certain systems if you know them well enough. And then a little bit about stochastic computation. It's sort of 50 years old and really quite relevant today. So hopefully it's useful. I always have a habit of putting too many things in my presentations because I'm like really excited about talking about things, which tends to mean that I don't get to the end. But I would prefer discussion and questions than sort of everybody falling asleep. So if there's questions and things, then please go ahead and ask. So neuromorphic engineering is about 30 years old now, maybe a bit older if you kind of, you know, kind of burrow into Carver Mead's head and sort of work out when he was first thinking about this. But it's fairly young in the scheme of things, really. It was kind of started at Caltech, and the story goes that Carver Mead was having a discussion with Max Delbruck, who was a Nobel Prize-winning biochemist. And Max was kind of fascinated with these new things, these newfangled things called transistors. And he sort of you know, they sort of started discussions about the sort of similar properties of transistors and ion channels. And then at the same time, Carver and Richard Feynman and John Hopfield were teaching a course called The Physics of Computation at Caltech, which must have been awesome. And if I have a time machine, I'm doing that first. Then I'm going to have a look at the feathers on the dinosaurs. But that's really kind of where it all started. And you can see that these are kind of four of really influential people in terms of computation and sort of where we are right now. So it's kind of fitting that it was these guys that sort of worked to come up with this sort of grand idea of neuromorphic engineering. And certainly Carver Mead was the trailblazer in the field. So the basic premise was, and I've seen this now for like skyrmions and other things now, so it's all this sort of self-similar, as you go smaller, everything kind of looks the same. But it's this idea that an ion channel sort of switches from, you know, a closed state to an open state, and so does a transistor, and that's really where it all came from. And we've all got to remember this was back in the 80s, which isn't that long ago for some of us, but it's a long time in the context of CMOS and circuits. And back then it was, you know, it was plausible. They could, you know, model ion channels and build the brain. And that's really what the idea was. So there are and always have been two goals of neuromorphic engineering. And I think I've seen both of these goals here, which is great because it just makes sense, these goals. One is the science goal, to help you understand even just a little bit about the brain and computation and learning. And the other is an engineering goal. How can I make a gadget that's useful? You know, the next big thing. How can I do computation better? How can I change the world? That sort of thing. And all kind of neuromorphic engineering has sort of sat on the edge of that. Some people have focused more on the science than the engineering and vice versa. But as a general rule, it's been a sort of a 50-50 proposition since the start. So I didn't think you'd seen it enough. So here it is again, Moore's law. This time I got all the way up to 2016. So you can see that, I went to some effort to find this picture. So you can see that it keeps on going. And so we've all, well, us CMOS people have all made the argument, it's going to end, absolutely going to end, 20 nanometer comes along, absolutely going to end, 10 nanometer comes along, absolutely going to end. At some point it must end because it'll just reach the physical limits of atoms and that sort of thing, but it's quite impressive. And this is basically the mountain that we've been up against for a very long time. We keep saying that computing like the brain is going to be way better, and I think we all believe that. But the reality is that this just keeps on getting better and better and better, and you can't fight that. You can't go to a funding body or go to an industry partner and say, but we're much better, please. But so this is sort of where we're at. And whether it ends or not, it's still useful to consider different ways of doing computation. So when it does end, of course, everybody's putting their hands up as to who will fill the gap, so to speak. I think, as Mark was saying in his talk, it'll probably be a sort of a combination of something working with the existing infrastructure, just because it's just so expensive and so entrenched. And it just makes sense as a community to try to, jump on that ship if you can. But as I said before, there's also reasons to look at computation just for the sake of digital is very boring and unelegant, and what we're doing has got a lot of benefit and use in its own right. So the early days of neuromorphic engineering really concentrated a lot on sensors, which I guess is because we had a bit more information. It was sort of talking late 80s, early 90s. Even now it's difficult to measure the brain to get any idea of what's going on, whereas there was definitely more data on vision and hearing, and that's where all the models and effort went, which has always been kind of interesting to me because they're not really, especially the cochlea, it's a physical system. It's not really neuromorphic. It's an interesting system, but it didn't really touch on computation very much at all. There was a lot of pioneering work done in low power design, simply because there was a realization quite early on that if you're going to try to model all these ion channels, you're going to start using a lot of current very quickly. So you need to go as low power as you can, and that still exists today in whatever technology you use. Low power is our driving motivation. There was lots of neuromodeling simply because there was some data on how a single neuron works, integrate and fire. The integrate and fire model comes from, I think, 1909 or something like that. So it's a very well-known model. And so it was something that we could at least play with. A protocol for communications that is used still in neuromorphic engineering called address event representation. And I can't remember which speaker spoke about this, but it's basically our kind of cheat way of connecting things together. When you have an event, which is a spike, you capture the time of that event and you put it on a bus. And there are real fundamental problems with that. It's very unscalable. So a lot of the neuromorphic systems at work, they're not going to scale much further simply because that bus is just going to, it's going to be like the traffic model very, very soon. And so that is a real problem that neuromorphic is hitting up against now. And then there was some spiking computation. So this is not too long ago, back in 2008. I would say that this was sort of the landscape. So the big break for neuromorphic engineering was a Nature paper in 1991 with Carver Mead and Misha Mahold. And this is the output from their model, and this was the output from I think a cat recordings, and you can see, it looks pretty good. And can I say this is typical for a neuromorphic engineer to just go, yeah, this is our chip and this is our our cat. And this is sort of what neuromorphic was for a long time, just trying to copy what biology did, get the same outputs without really understanding, what is it useful for? What are we going to do with it? But this is 1991, and this is the first time, and so this was kind of a big deal. The circuits that they used were like really simple circuits. So this is a differential pair. You put a voltage here, and so a current is coming through here, and that current sort of, through Kirchhoff's current laws, these two currents have to add. So you can set another potential here. It can be a particular kind of potassium or something representing that, and then this would be your membrane voltage, and so it's a very simple model. I can already see, although this is me in 2018, I can see that this is going to take up a lot of power if you start to make lots of these. But it was kind of an elegant solution, a very simple problem. And the results are, you have to say, it looks pretty good. And so this was like neuromorphic on the wave. We're going to build a brain because we got it all figured out. The other sort of early stuff was on event-based cameras. My computer refuses to connect me to EDU room, so I can show the videos later. But event-based cameras are basically, if nothing is moving, then they give no output, and if they're basically change detectors. So if something moves in front of the field of vision, then you'll get spikes. Spikes that indicate the direction as well. So they're having a bit of a renaissance at the moment. They've got a lot of potential applications, obviously, with autonomous vehicles. There's also applications to monitoring near-Earth objects, because unlike sort of normal optics, which get completely drowned out by the sun during the day, event-based cameras, you can still detect, satellites and so forth spinning around the Earth. Which is quite useful. So they're definitely becoming more commercialized, and they definitely have some applications. And there's a few companies out now that sell these things, and a lot of research going into them. But it's taken 30 years to get here, which is interesting. And the other thing, of course, is the silicon cochlea. And we saw in the talk before that they're non-linear devices, and they're quite interesting computational elements in their own right. And it's an interesting system to model. I would debate about its neuromorphicness. It's more of a mechanical system, really, but it's definitely a useful tool, and it can be used in many different places. And lots of people have done silicon cochleas, and everyone's promised that they're going to make better hearing aids or cochlear implants or something like that. But our old friend, the digital guys, keep on making better processors, so it's never really taken off. So 30 years, there's been some commercialization. If anyone remembers the Logitech ball, that's actually a neuromorphic design. If you look at the little dots here, they're actually not uniform, and that was based on, I think, compound eye structures. It's kind of neat if you look into the history of it, but that was kind of the first thing ever that was commercialized from the neuromorphic community. There was one of Covermead's students, Lloyd Watts, started a company called Audience, which used cochleas, sort of computational cochleas, to do noise cancellation in mobile phones. And most people's mobile phone probably does employ this system. It got bought out by Knowles Microphones a few years back, but it's one of the few success stories of using a cochlea usefully. And then there's this guy, Mark Tilden. I don't know if anyone's got kids with toys, but he founded WowWee Robotics. And all he calls it biomorphic, but all the kind of the motors that he uses are really kind of low power and really cool. And all that stuff happened as part of the neuromorphic community. So. And then there's just recently the group in Paris that makes event-based cameras called the ATIS cameras. They've started with, as far as I know, a lot of money injected from Intel, a company called Pixium, which is supposed to develop these cameras. So, it's early days and late days all at the same time, but it's been a difficult road to kind of get anything. I kind of have missed out here on the kind of the leaps in terms of circuit design and that sort of thing that have come out of neuromorphic engineering. There's countless products that use circuit designs and things that were developed by the community just to keep power low. But these are kind of the big ticket items, and it's a small list, but you know, it will grow. So more recently, neuromorphic engineering has really shifted into, for a while there it was very much aligned with computational neuroscience and those algorithms, and then we had that big wave of deep learning and machine learning, and now it's very much linked with those communities. And there's obvious reasons why. We've seen it in a lot of the talks here today, well, for the whole week, but there's a lot of similarities between, you know, how you would put together an artificial neural network and how you'd do a more kind of biological one. There's a lot of similarities. There's neuromorphic processes, and of course we all know about True North. I mean, it's got impressive numbers, but it doesn't really do anything. And I mean that with all due respect. I mean, the way they're using it isn't, right? So it has these neurons on it that can be tuned and do interesting things, but nobody knows how to use interesting neurons. And nobody has the time to tune useful, you know, interesting neurons, and nobody has an algorithm that would use that. So it's basically used as integrated fire, you know, deep learning accelerator, and that's not what it's made for. So it's not really doing a good job of that either. And I hope there's nobody here that's like a really big fan.
So you mean it's lacking the proper algorithm, or the hardware is not working properly?
It's lacking an algorithm. A lot of the problems with neuromorphic, and I'm being completely honest with everybody here today, but a lot of the problems with neuromorphic is that we've built lots of hammers and we've never found any nails. And so True North is a perfect example of a beautiful engineering masterpiece that doesn't solve any problems. And this is just kind of a tale of kind of, it's sad, you know, because it's going to get lost, maybe. You know, like people have worked really hard on this, but we don't know what to do with it. So it's going to go in a box somewhere or displayed somewhere at IBM. Yeah, right. Yeah, it'll be in a museum. Yeah, and you feel like all the waste and all the great minds that worked on this sort of thing, and somebody failed to go, let's first decide on what it's good for before we build it. You know, so I think we should all do that. There's, I think Mark was saying, like, we should be building algorithms with our hardware, not building the hardware and then going, okay, where's my nail? Because we've done that and we're 30 years down the track and we haven't really built anything useful yet. And that's kind of the sad truth. There's lots of work now in spiking neural networks and machine learning and artificial intelligence, and it's not to say there's not lots of great work happening. But it's slow, and it's been hindered by the fact that at no point in the early days of neuromorphic engineering did we kind of get together and go, you know, how can we build these things? What useful thing do I want to do with it? What application could it be useful for? And how do I get the best out of my hardware instead of pinching things from computer science, which absolutely were not made for the hardware, and trying to force it into our hardware and get worse results? That's kind of been the story. Wow, so I'm going to leave now. Everyone seems glum. I mean, you know, I'm still doing it. It's just, it's worthwhile being candid at times. I've done this at Telluride, and they get very angry at me. So, anyway, so my early work was in silicon cochlea and silicon neuron design. My background is as a chip designer, so I was working in industry, designing cochlear implants, chips, and for some ridiculous reason, I thought it'd be a good idea to do a PhD, which it was, but you know, you all know. So the cochlea is a superly interesting guy. It's like a bony structure. It's a transducer basically. So you have the sound pressure moving your eardrum, which moves your 3 tiny, tiny bones here. And then the stapes is basically pulling in and out of something called the oval window. And it creates some fluid moving around inside there. And the cochlea itself, it's like a snail just because it's very space conscious. But if you kind of pull it out, it's a long membrane, which at the start is very, very rigid. So it responds really well to high frequencies. And at the end, it's very floppy, so it responds really well to low frequencies. It's a beautiful mechanical design that an electrical engineer decided to model in transistors. And it has these other nonlinear properties where it is always trying to maximize its signal-to-noise ratio. So you've all experienced it. You're in a very quiet place and your ears start ringing. That's your ears, trying to hear something and there's nothing there. If anyone's gone into an anechoic chamber, those things drive me nuts. My ears go, whee! And it's because of this whole non-linear effect. But they're really quite amazing. And it's all basically mechanical. So as that fluid passes by your inner hair cells, they deflect, open an ion channel, and then that creates, that channel then connects to a neuron, which then sends a spike. But it's this crazy mechanical system that is very elegant, and it does an amazing job. It's got a dynamic range of about 100 decibel SBL, which is none of our sort of technologies get anywhere close to this. It's beautiful. That's why we do neuromorphic engineering, because it's beautiful. I tried and failed. But the dynamics looked pretty good. So these here, I'm doing the usual neuromorphic thing, showing you measurements, this time from a chinchilla, because we do not discriminate against mammals. We like to take measurements from them all. So this is what I'm talking about by how awesome the dynamic range of the ear is. So here we've got, when the input level is very, very soft, the cochlea, it tunes itself and becomes very sharp. And this is frequency along here. So it's getting rid of as much noise as it can, and it is given as much gain to the signal that it's trying to hear. And so my cochlea exhibited similar dynamics, but failed greatly on its ability to get anywhere near what the cochlea does. But it sort of, the interesting part of the cochlea was that it was oscillators that were coupled together, which was quite difficult to do. And yeah, so I implemented it in 0.5 and 1.2 micron technology. It sounds huge now. It's like a roadway. Yeah, so I mean, it looks okay. But the ugly truth is that it was highly unstable. Someone would breathe, and I'd be measuring, and then it'd all go into chaos and oscillations. And so it was really difficult to sort of get it working properly. There was about 30 parameters that I had to tune, and I used like potentiometers, so I was always sitting there changing potentials. And it was current mode and sub-threshold, and it was very noisy. Each of the sections were totally mismatched, and it was an absolute nightmare to work with. Does anyone want to do one with me now? I mean, I learned a lot from it, but it was an exercise in extreme patience and hitting a head against one. I had the maths right. I just couldn't implement it in the hardware to get anything kind of useful out of it. Yeah, so the other work was on neurons, and sorry.
Are you aware of when was that work done here?
2004, 2002.
What you are describing is exactly what the cochlea does, which is to sit at the critical point and achieve this large dynamic range.
Yeah.
Generically speaking, because it's at the critical point.
Yeah.
One of the major contributions in the cochlea physiology in recent years has been the work.
Yeah, I cited him greatly. Yes.
And Marcelo Mañasco,
Yeah.
which have demonstrated that indeed these difficulties that you have to tune
Yes.
your many oscillators to the critical point is naturally solved by our ears
Yeah.
solving these instabilities. So you have confessed about seeing this instability, but I think that you have to recognize that it's a beautiful demonstration that criticality allows you to build this 120
Yes, and when I saw your talk, I was like, it's spot on. I believe everything you say because this works. It's just about. I mean, I know so much more than I did then. I approached the problem from an engineering point of view. I knew what I wanted my output to look like, so I built a circuit, and it had those properties. And then I looked at the literature, and I saw Hudspeth and all these other people had described it, and it was kind of like, wow. Yeah, but I mean, but I need to get it working in hardware, and that's kind of the neuromorphic story, you know, like getting these things stable and working in a hardware system is really difficult. So that was that, and there was some good work done with it. I mean, one of the goals of neuromorphic, as I said in the first place, was a science goal. And one thing that we can do that sort of computational modeling doesn't do is change parameters in real time, and we can see how things interact. And so some of that led to some discovery about how the efferent connections from the brain into the cochlea control the tuning, which was really useful to know. But as I said, it was just really hard to build. And I think this idea of dynamical systems and having things built on critical points, it's very hard. We need some way of being able to work out how to implement these in our hardware in such a way that it's not, you know, it doesn't send you off the bridge with trying to tune thousands of parameters. So the other thing that was kind of big at the time was modeling neurons. I'm not sure why it became trendy. I think probably the work of Izikovic, who I saw it in somebody's slide, had a Izikovic neuromodel, but he basically took a lot of recordings from cortex and basically did like a curve fitting. I mean, it must be a very patient man, but then was able to describe a couple of nonlinear equations that describe the different properties that neurons can have. So then there was a bunch of other people, Mihalis and Niebuhr and Gerstner, and all sorts of different neuromodels came available. And then we all jumped on it and started to see if we could build these things. So these turned out to be a lot easier to build and get all the different behaviors. The problem was that we don't know what they're good for, and I guess that comes back to true north. It's got all these properties. The neurons can do all this, but you know, there's no algorithms for them. You know, it's not clear how to use this. But this is what neurons are doing. So we need some idea of, you know, what do we need as our computational element? What is important? I will say a side note on circuits. So I think, as I said, like yesterday's talk, it was yesterday, wasn't it? Yeah, on criticality. I fully support everything that was said and agree with it. I would, it's more of a semantic debate, but I would say that as engineers and physicists, we have to build circuits. I think they have to be parametric or tunable, otherwise they are rigid. I would argue also that any kind of trained neural network is a rigid system. Like they have a lot of use, they can do a lot of things, but once it's trained, it only does that one task. So it's not generalizable. So it has, you know, it has that rigid, I don't know what the word is, but it's not something that you can change then. So one of the arguments that I would make, and I've been making with everyone that I've been talking to, is that, you know, this sort of supervised learning is probably not the best approach to take. They do it really well in computer science. They do it really well in data science. It probably isn't something that we should be building systems for. What they don't do well is unsupervised learning. And unsupervised learning is what we need on our low-power gizmos. You know, these are things that can't Yeah.
Why would you say that?
Why would I say unsupervised learning?
Why we need unsupervised? I mean, I agree with you. You do not want backpropagation or, let's say, individual control of every connection by some external supervisor, but I don't see a fundamental problem in providing a reference. You know, you should get here.
Yeah.
Not. So
look, I don't have a problem with. I'm not saying don't do it. I'm just saying there's a huge hole in unsupervised learning, and it's an interesting place to go.
and why would you say this is then interesting to do in hardware?
Because that's the low power thing, right? Like in the future, everybody wants to have personalized stuff. Personalized. Tell me I'm about to get sick. Tell me that I'm dehydrated right now. Tell me, you know. And to do that, it has to learn you. We've had decades of like EEG data trying to predict epileptic seizures. But we're probably averaging out all the important bits because it's over populations, whereas probably the information is in an individual's data. And so you need a network to be able to train on an individual, right?
But that can still be supervised, no?
Yeah, I don't know how many people would be willing to come in every day, and it could be. You could have transmitted. Yeah, you could. Yeah. No, and I think reinforcement learning is a very useful. Absolutely. Yeah, having a teacher or a trainer is good.
That's what I mean.
Yeah. Oh yeah.
As soon
Okay.
as you have a teacher, it's supervised, no?
Well, it sits on that sort of uncomfortable area. Yeah. Yeah. So I mean, I'm just trying to be as controversial as possible. So is it working? So anyway, so neuromorphic engineering, after this experience of doing neurons and okay, yay, they work, but now what? And the cochlea and oh my goodness, this thing is difficult to tune. It came clear to me that it's really difficult to scale these things. And this is in CMOS, and this is where we have all the infrastructure, and this is where it's all kind of, and it's still really difficult to work in that domain. One of the biggest questions is how do we deal with all the connections? And the other thing is that sort of neuromorphic engineering promised this, the brain deals with lots of noise, and so if we copy the brain, we should be able to deal with lots of noise. And every time you read a paper, mine included, it would say, oh, it doesn't quite work because of noise and mismatch. And it sort of ran contrary to the reason why we were doing all this in the first place. And then there's the issue that digital continues to be cheap and reliable, and the power consumption keeps going down. And so it's this huge barrier to get over. There's the other problem just with getting people to work with your system. So the output of a neuromorphic system, there's events, it's asynchronous. It doesn't easily go onto your computer. You have to come up with some way to deal with it. And often for a long time, people were just framing it. And then it's like, what's the point if you're just going to frame event data? If the events are telling you something important, then you really ought to learn the events. So these were kind of problems that came to me, and I think a lot of people within neuromorphic engineering. And so there's definitely been a change since then. It should say that, I still do this, a lot of people still do this because it's still really expensive to do computation in digital, especially the kind of parallel pattern recognition computation. And that matrix multiplication is extremely expensive. And that coming up with ways to deal with that would be very helpful. And I think you need ways to deal with parallelization and sort of big matrix multiplication or whatever you use in its stead in order to do really truly intelligent computation. And I guess the other thing is that it's not elegant to do things in a sort of brutal digital way. And it feels like there must be a better solution because you look at that beautiful cochlea and you see what amazing feats it does. You think to yourself, surely with all our technology, we can come even a little bit close to that. If we kind of took the time to understand our problem and understand the hardware and the substrate that we're using for it. So sort of sent me on this sort of mission of, I was really sick of making excuses about noise and mismatch. So I was like, I need a solution. And I had been working with Jonathan Tapson for a long time, and I did my postdoc with him in Cape Town. And he had done a lot of work with, because he's a control systems guy, I looked at single neurons and their autocorrelation properties, and built some circuits doing cross-correlation using noisy neurons. And in those systems, he was injecting noise. He was making explicit changes to induce mismatch. So these were my kind of systems, you know. This is something I can play with. And then developed a neural ADC. I thought I was going somewhere else. I'll come back to the neural ADC in a bit. The other thing is that I kind of spent a bit of time away from neuromorphic and did industry stuff. And I mention this just because a lot of your systems could probably use time-to-digital converters to measure things. And in these regimes, if anybody here is using time-to-digital converters, things like dynamic element matching and random element switching to get rid of quantization noise is pretty common. And it dawned on me that it's kind of the same problem, but in a different domain. I'm kind of using mismatch, and I'm using randomness in order to get better results in a completely normal circuit. So it became clear that these things were kind of useful. We developed amplifiers using other people's original designs, but we developed amplifiers that could maximize the gain. And as a side thing, I used a cochlear as a spectrum analyzer. And I was thinking a cochlear in Spintronics would be kind of cool, and you could use it as a high-frequency spectrum analyzer. If anyone wants to talk to me about that later, that would be fun. So there was a lot of kind of other side projects going on that weren't really neuromorphic. But the neural ADC was, it's been kind of a theme now of ours. So you have a bunch of neurons, and the key point is that they're not synchronized. So one of them fires. So here, actually, it's a negative, so the threshold is down here. So it resets to a high voltage. I don't know why he did that. It's rather confusing. So here, a neuron will fire, and then you have an interneuron that just inhibits everybody else. And the result of this is that you kind of spread everybody else out. There's no clocks or anything like that. You're able to basically make sure everybody gets their turn, in a sense. So everybody is sampling the space, and they're doing it at really low frequencies. But together, as an ensemble, they're able to sample a much higher frequency waveform. So absolutely, shattering Nyquist. So this here was sampled with 4 neurons that were spiking at a rate of 10 kilohertz. 10 hertz, and these are 2 kilohertz waves. So it can be really cheap doing things this way. And it works quite nicely. So this was sort of the beginnings of, maybe we can do useful things with neurons after all. So then for some bizarre reason, I was given an opportunity to write a manifesto. I felt like I was a little young for a manifesto, but I grabbed the opportunity and wrote a manifesto anyway. And I tried to, I've been trying for a long time to work out what are the principles needed in order to use noise, or at least get around noise, because there's been a lot of work done by a lot of people, so it was kind of bringing it all together. So there's this concept of stochastic facilitation, where basically if you have enough small sampling elements that are all very highly unmatched, totally heterogeneous system, then you're able to get a lot more detail about the input. This is a complete toy here. This whole thing is completely designed for journal paper. But the idea is kind of the same. It's basically, if you have a lot of little elements, just like the ADC, if they're all decohered and they're all different, then they will give you information at different times and in different places about your world, whether it's a signal that you're trying to convert, whether it's a control algorithm, whether it's a recognition system. It's kind of the same sort of principles. The well-known sort of stochastic facilitation is stochastic resonance, and that has been used in a lot of systems. And it's just this idea that if you have sub-threshold signals at the threshold of where you can convert them into a digital signal, if a little bit of noise, and this sort of shows that there's some sort of sweet spot, allows you to get some information out about your signal. And so these signals can be very low power, and they've been used and commercialized in many different areas, but it is quite elegant. I mean, it comes with the problem, and I guess we saw it with the reservoir computing as well, that there's this sweet spot somewhere, and you need to work out what that sweet spot is. And again, that comes to knowing your hardware, making sure that you develop your circuits based on what you know about your hardware. It's difficult. There probably is an answer to where these sweet spots are, but it is a difficult problem. And as an engineer, that's not really something I do. And then there's noise shaping, which happens a lot in biology. So neurons are kind of like asynchronous sigma delta converters, where they're pushing the noise into the high frequencies. And that's very common. That's used everywhere in CMOS design. So there's some well-known ideas, and also there's these other counterintuitive ideas where having elements that are quite different from one another gives you a much broader sample of whatever you're trying to look at, a sample of space. And I'm running out of time. So yeah, I guess one of the motivations for this as well was that we see in computer science that in order to make a lot of these things work, and we saw it in the equations for reservoir computing, that the variance, you need some variance term. You need to add in variance to your system, and it seems, and it makes your computer simulation take a long time because you need the variance, because your computer is so perfect, it has no variance. Yeah.
When you mean noise, you mean about variability, or you mean terminal noise, or you mean bus?
Both. Yeah.
Bus, okay.
I'm just putting them in the same bucket. Yeah. And I guess depending on, again, your hardware and where you're operating, different noises will affect you more than other types of noise. You know, like it's any kind of variation is suppressed in our normal computing systems. Whereas if we kind of work out ways to use it, we might be able to do the kind of interesting computation that we want to do, but use what variance and heterogeneity in the system itself to do the computations, rather than have to put it in the end anyway. And it could speed things up quite a lot as well. So a proper neuromorphic processor, which included variance and heterogeneity in elements, it would be faster because you don't have to add in noise artificially. But then you'd need to know your system, because we've seen the amount of noise that you need is important. So, running out of time. So another system that we built was called competitive control. Here we use it as for tracking. So we have a bunch of neurons. We have 9 neurons here. If the target is blocking any of the receptors, then the spike doesn't come back. And that's the only thing we have. If I send a spike, does it come back? And the learning algorithm is basically, if I sent a spike and the spike came back, then I'm going to increase or decrease my threshold. I'm going to spike more. Okay, so I'm going to become more powerful in the system. And it's a very simple learning rule, but it allows you to do control without any controller. So it's all kind of works itself out. And the only issue with it is that you have to make sure that each one of these elements is not synchronized to each other. And then you'll be able to sample the world and have a control algorithm, in this case, which moves our eye so that it's always, so that the thing we're tracking is on neuron 5. And if it happens to be there, then we move in the direction where we thought it was going. It's a very simple algorithm that does really energy efficient tracking of something. and that doesn't use a controller. There's no controller, there's no learning. It just does its thing. So these are, it's kind of ridiculous showing these pictures, but these are basically showing that the fly starts off covering the eye, and then it moves here, and then we readjust, and it's in the middle, and you can sort of see how we're tracking the fly as it moves around. And the last one is unsupervised learning, and this is very much a toy, although maybe this is what got my engines running for unsupervised. Like last year, I think Jeffrey Hinton even in an interview said that that's the future, and I think that it is too. It's just really hard. I think reinforcement learning is completely appropriate and probably more something we can do because it's difficult to get these systems to work. So this system is looking at spatiotemporal patterns. So spikes coming in and particular patterns representing something. So it could be an image, and you create spikes for when there's a black versus a white or a white versus a black pixel. So you can convert your image into spikes, and then what this thing does, probably on the next page is better. So the learning rule is basically this: when you get a spike at the output, and this spike is a summation from all the different synapses. When you get a spike, you change these kernels or these sort of synaptic weights on the input. And if I spiked and I was going negative and this was still high, then I spiked too early. So the next time you spike a little bit later. And it just kind of tracks like that. It's a really simple learning rule. The only thing that you have as an input is the spike at the end. You don't know what the other spikes were doing. You just know what you did. If you spiked, the output spiked, and you change your rate, I guess, of learning, so how steep. And it learns until it's very, very highly tuned. And you can play with this, obviously, by playing with your threshold, but it can become a very highly tuned system. So even quite similar patterns, once it gets to this point, aren't gonna make this neuron fire. And so it learns that pattern. You've got a bunch of neurons in the chip. You can learn a bunch of patterns. It has properties similar to Bayesian inference, where our receptive field is basically it's doing sort of a quasi-posterior calculation. So if this was the receptive field and you don't get a spike, then you widen your receptive field to try to catch something. And then once you catch something, then you start to tune yourself because you're getting knowledge about the system, and then you kind of get this nice tuned response. So it's almost like a tracking algorithm. It's a toy that works really quite well. So we've been using it to do feature extraction. So these are pictures from single photon avalanche diode arrays. So they're 32 by 32 arrays. And we've got planes falling in front of the camera, and we're able to extract features as the plane's dropping and do recognition. So we kind of find the features as the planes drop. It's actually very fast. And then we use a regular neural network, a trained neural network at the end to do classification. So you can see that doing it this way, extracting these very kind of poor images and then extracting these little features, we're able to generate a lot less data. Like, that's a huge thing. This is orders of magnitude less data than doing it on an image. Even a 32 by 32 image, actually kind of segmenting it and doing the feature extraction is quite computationally heavy. So it's still a small problem, but it's a neuromorphic one that seems to work and is actually giving quite good benefits. So, like, I'm still learning, but some of the principles are that you need at least an ability to have your elements decohere. There's definitely times for synchronization in terms of like weight normalization is a huge problem in neural networks, and synchronization seems to be linked to that. So there's a whole heap of things we don't know. But for these toy examples I've given, some kind of decoherence is important. Random spreading, and I think we saw that with the reservoir networks, where if you can have your signal spreading enough, you know, if you can capture enough of that input space, then you can get quite nice results. And that's what this spreading is doing. So a lot of the stuff I do here, it's sort of temporal spreading, but it's the same as spatial spreading. So spreading out the reach of each neuron, even if it's just a little bit of touch to a larger space, will give you a much better network. And inhibition, so being able to turn off paths, it just helps learning. So finally, I might actually get through this thing. Stochastic computation. Now this is slightly different, and it comes from the 1960s, so it's 50 years old. If you read this paper, so I should have put the citation up there, but they all fell off the bottom last night, and it was very late. But I will give it to anyone that's interested. If you read it, it's like you're reading something somebody wrote today. It's the same problem. It's how do we do pattern recognition, parallel computation. Digital doesn't do it well. This is back when digital were vacuum tubes. And so what happened was the integrated circuit happened, and then, you know, they got good, and CMOS came along, and they forgot about this, and now we've got the same problem again. 50 years later, we're like, how do we do parallel computation? So this is a really interesting starting place, at least. And we've seen so many times people replicating work of the past and not realizing it was out there. So it's good that people have found this, because it would be a shame to have lost it. But the main idea is to represent numbers as probabilities. And so they fall in an interval of 0 to 1. So the numbers are represented by bit streams, so it is compatible with digital. So for instance, probability of a half is represented by half of the bits being turned on. So this is 8-bit number, so 4 of the bits are ones. And it doesn't matter where they're ones. And that's really important. It makes it really good for fault tolerance. So in digital, if you lose the first bit, if there's an error, you know, there's a big difference between the numbers. And I use 4 bits, but imagine it was a 64-bit number. Like the difference is massive. Whereas in stochastic computation, and certainly as you add more and more bits, losing a bit here and there is not a problem. So it's quite nice from that point of view. In order to create them, though, we do need random number generators. And there's been a lot of those, and actually there's been some papers of people using MJTs to create random numbers. So it's out there. And there's sort of cellular automata that you can use that do a really good job of getting fairly true random numbers. So that's not a huge issue. In order to create a stochastic number from a binary one, you basically just put them into a comparator, and if the random number is less than the binary number, you spit out a stochastic number. And I should have really done a simulation on that so I could prove it to you, but I'm just going to ask you to believe me. Okay. And then if you want to go the other way, it's basically just a counter, because the number of ones you have is the number that's being represented. So it's really easy to do multiplication. This is what seems to be the huge attractor for me and several other groups out there. It's an AND gate. One AND gate, you can do a multiplication, which is really cool. I'll show you what an AND gate looks like in digital, because there's a lot less cool faces here than if I was in a room full of... And addition is done with a multiplexer. So, and this here is a random number. So a random number flicks between the two inputs. Because it's a probability, you can't have more than one. So when you're adding two numbers together, it gets scaled by a half. And if you add 3 numbers together, it gets scaled by a third, and so on and so forth. So I did do a simulation here. So if I've got a stochastic number of a half and 0.75, If I want to multiply them together, this is the result I want. If I use 32 bits, which I did in this simulation, then the answer should be 12, and it's the blue here. And you can see it's moving around, but its average is 12. So the output of the number is quite noisy, but that's actually pretty cool. I never said it was going to be accurate. I just said it was. And this is just 32 bits. So, and 32 bits is equivalent to like 5 digital bits. So you kind of get a, you need long bit streams in order to get similar resolution. And so here is addition in the green, and addition's even more noisy because you've got the addition of that random signal flipping the multiplexer. So conventional multipliers, and the thing that is the bane of every digital designer out there is they're huge, massive things. So if you get an FPGA, there's only a limited number on the FPGA, and you have to kind of time multiplex, and you have to be very careful to not use too many. Whereas here, it's an AND gate, very small. So these guys, one of these guys is like 2 AND gates. That's for one element of an array to add 2 4-bit numbers. So this is very, very promising, I think, from the point of view, even if we want to do a neural network using skyrmions and then do the matrix multiplication, if we had a system that did it in stochastic computation, it would be a very low power system, even if you did have to go into the digital domain. So it's an interesting thing to look at. So so stochastic computation is really interesting in terms of saving digital hardware, where area is really very precious. So we saw that even Google's whiz-bang tensor processing units, I think it was 200 kilohertz that they're working at. So any kind of gains in terms of speed and area and putting more computations onto a chip is good. And the fault tolerance is excellent. And it's very noise tolerant. So I've been working on a stochastic, analog to stochastic converter. And if I have, if I just do it kind of with non-noisy what's the word I'm looking for? If I change into stochastic numbers without any noise, then I basically get 3 bits accuracy compared to, it's basically a 3-bit accurate ADC. If I add noise into there, though, I can get like really close, and then I can reconstruct signals really accurately, even though I'm using just 8 bits of stochastic computation. So it sort of shows that if we embrace this noise, it can help us. In conclusion, I'm almost going to make it. So neuromorphic, I was kind of harsh at first, and through the talk, I've grown to love it again. It's at a crossroads. It's been a difficult journey for people in neuromorphic, and it started off looking like this was going to be something we can do, and then we realized that it's a very hard problem that we're trying to solve. Hardware algorithms need to be developed with the hardware in mind, and it doesn't matter what substrate you're using. I think you need to start thinking about what you're going to do with your device, and you need to start thinking of ways that you can use it for that task. The algorithms that I showed are very area efficient and power efficient, and they were developed that way because I was thinking about the hardware when I did it. And other people, and there's a long list of people that are doing similar things, also have gotten good gains by being mindful of the capabilities of their hardware. And stochastic computation is quite an interesting new way to represent values that doesn't move us too far away. Like there's not a huge overhead to using stochastic computation, so we should consider that. I will thank my collaborators, Saeed, who's writing up his thesis right now, Chetan, who is now at the Indian Institute of Science, John Tapson, who's AWOL, Andrew Nicholson, who's my former PhD student and postdoc, and Gaetano, who's done lots of work for this. Thank you for your attention.